A dielectric material is an electrical insulator that can be polarized by an applied electric field. When a dielectric is placed in an electric field, electric charges do not flow through the material as they do in a conductor, but only slightly shift from their average equilibrium positions, causing dielectric polarization. Because of dielectric polarization, positive charges are displaced toward the field and negative charges shift in the opposite direction. This creates an internal electric field that reduces the overall field within the dielectric itself. If a dielectric is composed of weakly bonded molecules, those molecules not only become polarized, but also reorient so that their symmetry axes align to the field. The study of dielectric properties concerns storage and dissipation of electric and magnetic energy in materials. Dielectrics are important for explaining various phenomena in electronics, optics, and solid-state physics. Terminology. While the term insulator implies low electrical conduction, dielectric typically means materials with a high polarizability. The latter is expressed by a number called the relative permittivity. The term insulator is generally used to indicate electrical obstruction, while the term dielectric is used to indicate the energy-storing capacity of the material. A common example of a dielectric is the electrically insulating material between the metallic plates of a capacitor. The polarization of the dielectric by the applied electric field increases the capacitor's surface charge for the given electric field strength. The term dielectric was coined by William Whewell in response to a request from Michael Faraday. A perfect dielectric is a material with zero electrical conductivity, thus exhibiting only a displacement current. Therefore, it stores and returns electrical energy as if it were an ideal capacitor. Electric susceptibility. The electric susceptibility (Ki) of a dielectric material is a measure of how easily it polarizes in response to an electric field. This, in turn, determines the electric permittivity of the material and thus influences many other phenomena in that medium, from the capacitance of capacitors to the speed of light. It is defined as the constant of proportionality relating an electric field E to the induced dielectric polarization density P, such that where epsilon 0 is the electric permittivity of free space, the susceptibility of a medium is related to its relative permittivity epsilon r by. So in the case of a vacuum, the electric displacement D is related to the polarization density P by dispersion and causality in general. A material cannot polarize instantaneously in response to an applied field. The more general formulation as a function of time is that is, the polarization is a convolution of the electric field at previous times with time-dependent susceptibility given by Chi. The upper limit of this integral can be extended to infinity as well if one defines Chi equals 0 for delta t less than 0. An instantaneous response corresponds to Dirac delta function susceptibility Chi equals Chi delta. It is more convenient in a linear system to take the Fourier transform and write this relationship as a function of frequency. Due to the convolution theorem, the integral becomes a simple product. Note the simple frequency dependence of the susceptibility, or equivalently the permittivity. The shape of the susceptibility with respect to frequency characterizes the dispersion properties of the material. Moreover, the fact that the polarization can only depend on the electric field at previous times equals 0 for delta t less than 0, a consequence of causality, imposes Kramers-Kronig constraints on the real and imaginary parts of the susceptibility Chi. Dielectric polarization. Basic atomic model. In the classical approach to the dielectric model, a material is made up of atoms. Each atom consists of a cloud of negative charge bound to and surrounding a positive point charge at its center. In the presence of an electric field, the charge cloud is distorted, as shown in the top right of the figure. This can be reduced to a simple dipole using the superposition principle. A dipole is characterized by its dipole moment, a vector quantity shown in the figure as the blue arrow labeled m. It is the relationship between the electric field and the dipole moment that gives rise to the behavior of the dielectric. When the electric field is removed, the atom returns to its original state. The time required to do so is the so-called relaxation time, an exponential decay. This is the essence of the model in physics. The behavior of the dielectric now depends on the situation. The more complicated the situation, the richer the model must be to accurately describe the behavior. Important questions are: is the electric field constant or does it vary with time? At what rate? Does the response depend on the direction of the applied field? Is the response the same everywhere? Do any boundaries or interfaces have to be taken into account? Is the response linear with respect to the field, or are there non-linearities? The relationship between the electric field D and the dipole moment m gives rise to the behavior of the dielectric, which for a given material can be characterized by the function f defined by the equation. When both the type of electric field and the type of material have been defined, one then chooses the simplest function f that correctly predicts the phenomena of interest. Examples of phenomena that can be so modeled include refractive index, group velocity dispersion, birefringence, self-focusing, harmonic generation, dipolar polarization. Dipolar polarization is a polarization that is either inherent to polar molecules, or can be induced in any molecule in which the asymmetric distortion of the nuclei is possible. Orientation polarization results from a permanent dipole, e.g., that arising from the 104.45 degrees angle between the asymmetric bonds between oxygen and hydrogen atoms in the water molecule, which retains polarization in the absence of an external electric field. The assembly of these dipoles forms a macroscopic polarization. When an external electric field is applied, the distance between charges within each permanent dipole, which is related to chemical bonding, remains constant in orientation polarization. However, the direction of polarization itself rotates. This rotation occurs on a time scale that depends on the torque and surrounding local viscosity of the molecules. Because the rotation is not instantaneous, dipolar polarizations lose the response to electric fields at the highest frequencies. A molecule rotates about 1 radian per picosecond in a fluid, thus this loss occurs at about 1011 Hz. The delay of the response to the change of the electric field causes friction and heat. When an external electric field is applied at infrared frequencies or less, the molecules are bent and stretched by the field and the molecular dipole moment changes. The molecular vibration frequency is roughly the inverse of the time it takes for the molecules to bend, and this distortion polarization disappears above the infrared. Ionic polarization. Ionic polarization is polarization caused by relative displacements between positive and negative ions in ionic crystals. If a crystal or molecule consists of atoms of more than one kind, the distribution of charges around an atom in the crystal or molecule leans to positive or negative. As a result, when lattice vibrations or molecular vibrations induce relative displacements of the atoms, the centers of positive and negative charges are also displaced. The locations of these centers are affected by the symmetry of the displacements. When the centers don't correspond, polarizations arise in molecules or crystals. This polarization is called ionic polarization. Ionic polarization causes the ferroelectric effect as well as dipolar polarization. The ferroelectric transition, which is caused by the lining up of the orientations of permanent dipoles along a particular direction, is called an order-disorder phase transition. The transition caused by ionic polarizations in crystals is called a displacive phase transition. Dielectric dispersion. In physics, dielectric dispersion is the dependence of the permittivity of a dielectric material on the frequency of an applied electric field. Because there is a lag between changes in polarization and changes in the electric field, the permittivity of the dielectric is a complicated function of frequency of the electric field. Dielectric dispersion is very important for the applications of dielectric materials and for the analysis of polarization systems. This is one instance of a general phenomenon known as material dispersion, a frequency-dependent response of a medium for wave propagation. When the frequency becomes higher, dipolar polarization can no longer follow the oscillations of the electric field in the microwave region around 1010 Hz. Ionic polarization and molecular distortion polarization can no longer track the electric field past the infrared or far infrared region around 1013 Hz. Electronic polarization loses its response in the ultraviolet region around 1015 Hz. In the frequency region above ultraviolet, permittivity approaches the constant epsilon-0 in every substance, where epsilon-0 is the permittivity of the free space. Because permittivity indicates the strength of the relation between an electric field and polarization, if a polarization process loses its response, permittivity decreases. Dielectric relaxation. Dielectric relaxation is the momentary delay in the dielectric constant of a material. This is usually caused by the delay in molecular polarization with respect to a changing electric field in a dielectric medium. Dielectric relaxation in changing electric fields could be considered analogous to hysteresis in changing magnetic fields. Relaxation in general is a delay or lag in the response of a linear system, and therefore dielectric relaxation is measured relative to the expected linear steady-state dielectric values. The time lag between electrical field and polarization implies an irreversible degradation of Gibbs free energy. In physics, dielectric relaxation refers to the relaxation response of a dielectric medium to an external, oscillating electric field. This relaxation is often described in terms of permittivity as a function of frequency, which can, for ideal systems, be described by the Debye equation. On the other hand, the distortion related to ionic and electronic polarization shows behavior of the resonance or oscillator type. The character of the distortion process depends on the structure, composition, and surroundings of the sample. Debye relaxation. Debye relaxation is the dielectric relaxation response of an ideal, non-interacting population of dipoles to an alternating external electric field. It is usually expressed in the complex permittivity epsilon of a medium as a function of the field's frequency omega, where epsilon infinity is the permittivity at the high frequency limit. Delta epsilon equals epsilon s minus epsilon infinity, where epsilon s is the static, low-frequency permittivity, and tau is the characteristic relaxation time of the medium. This relaxation model was introduced by and named after the physicist Peter Debye. Variants of the Debye equation. Cole equation. This equation is used when the dielectric loss peak shows symmetric broadening. Cole-Davidson equation. This equation is used when the dielectric loss peak shows asymmetric broadening. Havre-Liak-Negami relaxation. This equation considers both symmetric and asymmetric broadening. Cole-Rausch-Williams-Watts function. Paraelectricity. Paraelectricity is the ability of many materials to become polarized under an applied electric field. Unlike ferroelectricity, this can happen even if there is no permanent electric dipole that exists in the material, and removal of the field results in the polarization in the material returning to zero. The mechanisms that cause paraelectric behavior are the distortion of individual ions and polarization of molecules or combinations of ions, or defects. Paraelectricity can occur in crystal phases where electric dipoles are unaligned and thus have the potential to align in an external electric field, and weaken it. An example of a paraelectric material of high dielectric constant is strontium titanate. The limbo 3 crystal is ferroelectric below 1430 K, and above this temperature it transforms into a disordered paraelectric phase. Similarly, other perovskites also exhibit paraelectricity at high temperatures. Paraelectricity has been explored as a possible refrigeration mechanism, polarizing a paraelectric by applying an electric field under adiabatic process conditions raises the temperature, while removing the field lowers the temperature. A heat pump that operates by polarizing the paraelectric, allowing it to return to ambient temperature, bringing it into contact with the object to be cooled, and finally depolarizing it, would result in refrigeration. Tunability. Tunable dielectrics are insulators whose ability to store electrical charge changes when a voltage is applied. Generally, strontium titanate is used for devices operating at low temperatures, while barium-strontium titanate substitutes for room temperature devices. Other potential materials include microwave dielectrics and carbon nanotube composites. In 2013, multi-sheet layers of strontium titanate interleaved with single layers of strontium oxide produced a dielectric capable of operating at up to 125 GHz. The material was created via molecular beam epitaxy. The two have mismatched crystal spacing that produces strain within the strontium titanate layer that makes it less stable and tunable. Systems such as BAR1-XSRXTIO3 have a paraelectric ferroelectric transition just below ambient temperature, providing high tunability. Such films suffer significant losses arising from defects. Applications. Capacitors. Commercially manufactured capacitors typically use a solid dielectric material with high permittivity as the intervening medium between the stored positive and negative charges. This material is often referred to in technical contexts as the capacitor dielectric. The most obvious advantage to using such a dielectric material is that it prevents the conducting plates, on which the charges are stored, from coming into direct electrical contact. More significantly, however, a high permittivity allows a greater stored charge at a given voltage. This can be seen by treating the case of a linear dielectric with permittivity epsilon and thickness d between two conducting plates with uniform charge density sigma epsilon. In this case the charge density is given by and the capacitance per unit area by. From this, it can easily be seen that a larger epsilon leads to greater charge stored and thus greater capacitance. Dielectric materials used for capacitors are also chosen such that they are resistant to ionization. This allows the capacitor to operate at higher voltages before the insulating dielectric ionizes and begins to allow undesirable current. Dielectric resonator. A dielectric resonator oscillator is an electronic component that exhibits resonance of the polarization response for a narrow range of frequencies, generally in the microwave band. It consists of a puck of ceramic that has a large dielectric constant and a low dissipation factor. Such resonators are often used to provide a frequency reference in an oscillator circuit. An unshielded dielectric resonator can be used as a dielectric resonator antenna. Some practical dielectrics. Dielectric materials can be solids, liquids, or gases. In addition, a high vacuum can also be a useful, nearly lossless dielectric even though its relative dielectric constant is only unity. Solid dielectrics are perhaps the most commonly used dielectrics in electrical engineering, and many solids are very good insulators. Some examples include porcelain, glass, and most plastics. Air, nitrogen and sulfur hexafluoride are the three most commonly used gaseous dielectrics. Industrial coatings such as parylene provide a dielectric barrier between the substrate and its environment. Mineral oil is used extensively inside electrical transformers as a fluid dielectric and to assist in cooling. Dielectric fluids with higher dielectric constants, such as electrical-grade castor oil, are often used in high-voltage capacitors to help prevent corona discharge and increase capacitance. Because dielectrics resist the flow of electricity, the surface of a dielectric may retain stranded excess electrical charges. This may occur accidentally when the dielectric is rubbed. This can be useful, as in a Van de Graaff generator or electrophorus, or it can be potentially destructive as in the case of electrostatic discharge. Specially processed dielectrics, called electrets, may retain excess internal charge or, frozen-in, polarization. Electrets have a semi-permanent electric field, and are the electrostatic equivalent to magnets. Electrets have numerous practical applications in the home and industry. Some dielectrics can generate a potential difference when subjected to mechanical stress, or change physical shape if an external voltage is applied across the material. This property is called piezoelectricity. Piezoelectric materials are another class of very useful dielectrics. Some ionic crystals and polymer dielectrics exhibit a spontaneous dipole moment, which can be reversed by an externally applied electric field. This behavior is called the Ferroelectric Effect. These materials are analogous to the way ferromagnetic materials behave within an externally applied magnetic field. Ferroelectric materials often have very high dielectric constants, making them quite useful for capacitors.